you, and hello everyone. Today I'll be talking about the topic already mentioned by Anna. Thank you for that. And to start with it, first, what is a network? Does anyone of you want to answer that? Yes? Sure? That's a wonderful answer. Anyone else? Okay. In words of my professor Ulrich Brandes, who I worked with a while back, network is not a graph, it's a data. To elaborate it more, networks are data on diodes. If you didn't notice before, it's actually even I didn't notice before. It says on a diode. Apparently, it's supposed to be a pun for on a diode. Anyways, what is a diode? According to this quick Google search, it is something that consists of two elements or parts. In the context of networks, diode looks something like this. You have 2 points, or 2 nodes as we call them, and there is a line connecting them. This line can be undirected or directed. There can be multiple between 2 nodes. One of them can be directed, the other one can be undirected, and so on and so forth. There are many, many combinations available. And where is all the data? So same thing from the previous slide. We have these 3 components. And we can also think of this one thing as a whole network already. It's a network of 2 nodes and 1 edge, which can also be scaled up to many nodes, many, many edges, and so on and so forth. And we can have data on the edge, link, diode. People call it different things. You can choose your favorite. We can have it on the node or the whole graph. These are places to put data. In the network science community, at least, we call data on nodes as node attributes. We have edge attributes, and we can have graph attributes. Okay, oops, it wasn't supposed to be there. You can ignore it for now. But what do you think that kind of structure would be called? Oops. There was supposed to be an answer, but it's a triad, as you might see on the side already. And the structure on the right is an open triad. Now, why am I mentioning this? Because we have another really good name for it, called a forbidden triad. Any guesses why it's called forbidden? Okay, that's what I'm here to tell you. Sorry, was... Okay, so that is actually in the right direction. Green can talk to blue. That's why it is open. But in real world, we observe that green does talk to blue at least a bit. And we call it a weak link. So if you see on the left, A and C are connected, A and B are connected through formal relationships. But in the real world, we observe that if there are 2 strong ties here, it's very rare that there won't be at least a weak tie between B and C. You can take an example of just a friend group. So one of them brings someone else to that group to talk about, just hang out normally. And you would observe that there is a weak tie slowly forming between members of the group and the external person who was just added there. On the right, you can see we again have some small groups here, and there are weak links connecting them through some other people. In real world, let's take an example of Facebook. This map here tells us how Facebook looked like in 2000, the first decade of 2000s. I don't remember the exact year. Does anyone want to take a guess how many monthly active users does Facebook have? Yes? A billion, okay. Anyone else? Have you heard of the experiment where if multiple people answer the same question, the average tends to be close to the real answer? We can test that. So we have 1 billion and 2 billion, okay. 3.5, okay. 500,000. So could you repeat that? 500 million, okay. So you're 1, 2, half, 3.5. Okay, the right answer is 3 billion, and it's growing continuously, if I remember correctly. So I think one of the people here, you were right, thank you. It wasn't the average this time, it was the maximum number that was suggested. But that's okay. So why am I showing you Facebook suddenly? Connecting to our previous slide about weak and strong links, there was this paper called The Role of Social Networks in Information Diffusion. And 3 out of 4 authors were with Facebook, so they had access to all the data that researchers like us don't usually have. So of course, they can analyze it even more. And they realized that the percentage influence on feed with weak and strong ties is as follows. So if we look at the tie strength for comments, messages, photos, and threads, we do see that weak ties, which are probably with more people than strong ties, do considerably influence our Facebook feeds and eventually our behavior as well. And coming to influence, I have a very interesting picture to show. How many of you have seen this before? Or something similar? Okay. Now, we can understand this through networks as well. We can understand everything through networks, in my opinion. Over here, we have attributes of people. In this case, it can be, for example, hair. Okay, and for most of them, it's hair. And on the other hand, we can have a completely different side where we first look at ties and then see how they changed attributes. So in the first one, people look for someone who's similar to them with similar attributes. That led to them forming a tie. In this case, maybe adopting a pet dog who looks like them. On the other hand, let's assume they were friends already, and one of them decides to dress up like this, and the other one adopted. To give you a real-world example, if any one of you saw me in like a pink hat, that was inspired by a person from last year who was wearing a green mask, and you all can also get influenced and come up with random stuff to wear. In formal terms, we call this property homophily, which means people tend to connect with others who are similar to them. And now that we're talking about people be people Inc., and influencing, here is one other example of a corporate network. So this was, okay, so the names are not real, they are just there to have something to talk about and also hide the real names. So assume there was this company called Halifax, which they were a large defense contractor on US's West Coast. And they have multiple divisions. We are concerned about the aircraft engine manufacturing divisions, specifically their internal auditing staff. Since a while, their performance was not really doing good, and also their manager chose to move on. In the past, they would just promote people within the team because they already knew how things work, and it'll be easier for other people to form working relationships with them. Overall, it just seemed like a smoother process to promote someone and for them to continue being a manager. But the comptroller of Halifax, called Sheila Jackson, again a fake name, she decided that the new manager should not be from within that unit. And she brings in Manuel, who was a manager in some other division for some other unit, but he was really amazing at his work and he improved the team performance a lot. Now, if we look at this graph, over here, the green ones, these are auditing teams. The yellow ones are secretaries. We have managers over here and manager of manager over here. And when Manuel just joined this team, he realized that even though the performance was suffering, but the auditors, people here, the green ones, they had basically no idea that their performance was lacking. And he realized that the main reason of performance being not so good is that there was very less coordination happening between these two and these two. So how the normal process works is the green ones, they get some files to audit, they do some site visits, they have a lot of paperwork. And to address that paperwork and do their job properly, they need coordination with the yellow people. Yellow people, okay. And so Manuel, since he was so concerned about the team, he thought, okay, let me try some restructuring. And he came up with the idea that he can assign a few of these secretaries to auditors. So for example, Kathy can be the secretary for Carol and Harold, and they will always go to her for all of their tasks and responsibilities. So here, Donna, who was in charge of all the secretaries, earlier her job was also similar to other secretaries, also like helping out people and doing their paperwork, things like that. But now, even though her role stayed the same, her responsibilities changed a bit. Now she was acting like a facilitator in case some problems arose, and things like that. So she was helping her team when they needed her, but her role as secretary was slightly limited. When these processes were implemented, within a week, the number of audits were same as projected. So okay, so for some context, earlier the number of audits were less than the projected. So that was the gap that was happening. So within a week, even though the numbers were fine, there were complaints happening everywhere in the team. And of course, Manuel was not happy because he just joined this team, and it's not a good thing. Plus, they also got a huge backload of paperwork, even though it wasn't directly related to audits, but they also had some other things on the side. Now, what does Manuel do? He finds Professor David Krackhart, who was the person who wrote the paper where this network was also introduced. Professor is a professional in networks, and he loves trying to analyze people, for example. He goes to all of them, and he asks 2 questions. The first one is, who among the other 13 people here in the auditing group do you typically go to for help or advice when you encounter a problem? And the second one, from the other direction, who typically comes to you for help or advice when you have a question or a problem at work? Now, he gets all of these survey answers and he uses them to create a graph or a network. And this is what it looks like. He arranged the nodes such that all the arrows, or he tried to maximize the number of arrows that are pointing upwards. Any first impressions from this graph? What was happening? Nancy is important. Even Manuel was going to Nancy. We see that Stuart and Charles, they were going to each other when they needed some help. Donna was often going to Manuel or Nancy. Nancy goes to Donna. There's like a very faint line over here. And if I see it correctly, the only arrow downwards is from Nancy to Donna. So Donna is also important to some extent, but we're focused on Manuel and Nancy for now. So Nancy is important. And what can be a potential solution for Manuel? Should he just promote Nancy to be the manager? Let's not go there. But there was a solution. They talk, because it's a good thing to have a conversation. And when the professor shared this graph or this network with Manuel, he was like, oh no, I completely forgot about her. I know she's important. I saw that with my eyes. So we're just translating those things that we see with eyes, which are some signals here and there, into something that you can see formally. And then we talk. They talk a lot for 2 months, and they try to come up with a solution. And Manuel asks her, are you happy with the current state of affairs? My bad. Yeah. Are you happy with the current state of affairs? And Nancy said no, of course, because things were not really working out. And that's when they arrived on a compromise, which was that they will not remove the current idea completely of assigning secretaries to different auditors, but they will change it just a bit. In this case, the compromise was that secretaries do have a say what they want to work on, and the assignments would be temporary. So it's not that Katie is always assigned to Harold and Carol. They can change based on what project they're working on, how the situation is, and if they are sick or not, things like that. So that tells us networks are amazing, which will also be the conclusion eventually, but step 1. Any questions till now? Or we can also have a Q&A in the end. Anything works. Now, I'll have even more examples of some fun networks. But before that, we have this thing called a core-periphery structure. It is also a type of network where we have a core, of course, where everything else is connected to everything else. Everything is connected to everything else in the core. So over here we have 8 nodes, and all 8 of them are connected to each other. And then we also have a periphery. Periphery nodes are only connected to other nodes in the core and not at all to each other. Now, let's learn about monkey networks. There was this paper called History of Free-Ranging Rhesus Monkeys of Silver Springs from 1987. By the way, I also have a year here because this field is ancient and it's wonderful. We have this guy called Edward, and there was a picture of this other monkey, but they didn't name her yet. And this is the network that we get. Any guesses on how we might arrive on that network by just observing the monkeys? That's a wonderful idea. So for those who didn't hear her, it was about grooming, like monkeys tend to groom each other. And there are actually networks which use this behavior. I think it was there for cows because even they tend to be a part of like grooming stuff. But in this case, they use something called a co-occurrence network. There was a pond in the forest, or more like a lake in the forest, where these monkeys lived. And whenever two monkeys were there at the same time, the strength of the edge between them increased by a certain amount. So over here, if you see, for example, these two nodes, they were at the pond together more often than these two nodes over here. And if we try to fit this network into the core-periphery structure that we saw, we see that there is a core, indeed, and a periphery. If I remember correctly, I think a few of these were like very strong moms, so hats off to them. And over there, we also see some dotted lines, which are the edges that were more on the weak side, or like the edges that can. Okay, so these edges existed, but they did not fit with the core periphery structure, because this one here should not be there because the periphery connects only to the core, not really to themselves. Now, on the other side, where one more example where we see a core periphery structure is international trade networks. A big jump, but networks are everywhere. Over here again, if you see, we have a bunch of countries that are more connected to each other than they are with things on their periphery. We do see this very thick line here between United States and Mexico, which is also obvious to some extent. But what's going on here? This network is from the year 2000. The paper was published in 2007. And there is a lot of trade going on with volume more than 10 billion US dollars. In the core, we see 17 countries. In the periphery, we have 56. So over here, we're trying to quantify how far is this network from an ideal core periphery network. In an ideal one, we won't have any edges between periphery nodes, like for example here, and everything in the core will be connected to everything else in the core. So over here, if you see, only 2.3% editing was required, which is derived from the number of edges missing in core and periphery. So yeah, good stuff. Now, one more spicy network, which is about what Moscow is to Russia. There was this paper in 1979 about the medieval river trade network of Russia, revisited. It was published in Social Networks, again, a very cool place. We have this map from the 12th to 13th century trade routes along rivers in Russia. And to see it clearly, we have this graph that was generated from that river network. And over here, we have Moscow. Just by seeing it visually, Moscow does seem to lie in a fairly good location. And the question we're trying to answer here is that, were there any other signals that can indicate that Moscow will be an important city in the centuries after? So over here, we want to quantify what is a good location. In the context of river trades, we want low travel distance, so anyone can reach there in shorter time, and ideally frequent stopovers. So for example, if someone is going from bottom left to top right, they should try to stop at Moscow, or like any other city that you want to look at. In this case, we quantify these with two metrics, so to say. First one is called intermediate node occurrence rate, which you can see here. It quantifies the number of times a node, Moscow, falls on a shortest path. If we try to find the shortest paths between all the nodes, so if you have n nodes, then like shortest path between all of them, then how many of those shortest paths have Moscow as an intermediary? That is our x-axis. So if we have more of these paths, it means we'll have more frequent stopovers. And the other thing we look at is aggregate distance of each shortest path from the node concerned. On the y-axis, you can see this distance for each shortest path. What it means in this case is the shortest path from Moscow aggregated or like summed over for all the shortest paths is fairly less as compared to others. So the y-axis value should be on a lower end. And if you look at Moscow on this plot, we do see a big difference between the city and other ones. So yeah, there were indeed some signals that we'll have frequent stopovers and we do have low travel distance, which is good for that. In formal terms, the low travel distance is somewhat similar to betweenness centrality, and frequent stopovers are called closeness centrality, or like just about the number of shortest paths that we can have from that node. Now, since we know the term centrality already, let's revisit the previous hierarchy we were looking at. Now we have another term called influence centrality, and if we calculate this for all the nodes in the graph we saw earlier, we do see this ranking. The values on the left over here, those are the values of influence centrality calculated for all of these nodes. And we do see that we don't necessarily need to try to point all the arrows upward if we have centrality. And that was the end of my examples of networks. To summarize, we learned a bit of many things. What is a network? It's data. The forbidden triad, strength of weak ties. So please network more in this conference as well. We have weak ties on Facebook, how they are influential. Then homophily, the dogs looking like people. Corporate hierarchies, monkey network, trade network, and why Moscow the way it did, or at least some signal towards it. Networks are beautiful, I love them, and they're very useful. Thank you, and also thank you to the professor who first introduced me to the world of networks.
Thank you so much. It's lovely to know about how networks work, right? Especially in corporate world. So a quick reminder, there is a microphone on your right. You can come up and put a question, or if you are too comfortable, then I can come up to you. All right.
I just get started. Okay. Thank you for the great talk. First of all, I'm no network specialist, so this might turn out very stupid. But from my knowledge of statistics, there's this general thinking of correlation does not automatically mean causation. So what I've seen today makes absolutely perfect sense, but how careful do you need to be when you build a network and try to draw a conclusion from them?
Oh my God, very careful. Because absence of an edge can mean you have incomplete data, or it can mean that the edge is actually missing. And there is a way to address this, but it's not usually taken into account. For example, where is the network again? Yeah, for example, over here itself, what if Donna just forgot about Charles? That Charles did come to her for help, or if she also went to Charles. So those things are always there, and we need to be very careful also in what exactly we're analyzing, because, for example, in huge graphs like that of Facebook, you have so many nodes and so many edges, like 3 billion plus people. And then you need to narrow down what you're looking at. So the sampling that's happening is also a very important step, because it can influence your results by a lot. I hope that answers your question.
Thank you for your talk. Do you have any favorite network or graphs?
Yes, I did not include it here, but there is one called Karate Club Network, if anyone has heard of it. There is actually a Karate Club where whoever mentions the Karate Club at a network conference first gets that award, and it gets passed on to the next person. But it's mainly limited to network science conferences. It's about how there was this karate club with an instructor and a manager, and how it split up because these two had some arguments going on, and who chose what side in that club. And it's amazing. Yes, thank you.
Do you have any recommendations for Python software to do network analysis?
Yes. So if you are just getting started with networks and you want to understand the concepts, NetworkX is pretty good. But in my opinion, it is kind of slow, especially when you're dealing with bigger networks. So I often go with NetworkKit. I think the documentation could be better in NetworkKit, but it's very fast. I remember a piece of code that was taking a few hours in NetworkX took like 5 seconds in NetworkKit, because NetworkKit is just a wraparound around a C++ implementation. So for starting, NetworkX, and then you can transition to NetworkKit. That would be my suggestion.
Thank you.
All right. So what's the second point on the plot with Moscow here? Sorry.
Yes.
You had the plot with Moscow on the
We
far right.
have-
Like, what's the second most rightward point in there?
I don't remember, but I think it was St. Petersburg. But I'm not sure, so don't quote me on that.
That would be cool.
Right? Networks are amazing, as I said.
Any more questions?
Any recommendation for graph databases?
Unfortunately, no. That is something I want to look at soon, but I haven't gone there yet. But let me know if anyone of you has any ideas. I would love to try it out. Thanks for the question, though.
Any other? We have some more time. Well, then my question is, what was the most surprising pattern that you found across different domains in which you worked? Like the most surprising pattern of network, if there was any.
I think paradoxes in general are pretty surprising, and one I can remember now is called friendship paradox, which was there in the introductory lecture of the course by the professor I mentioned. It's, if I remember correctly, it says that the mean number of friends your friends have is higher than the number of friends you have. That is a very vague paraphrasing, but it tries to quantify that you have less friends than the number of friends your friends have. There is a statistical reasoning to it, and you can all feel free to look it up. But it does seem surprising, and the main intuition was that you're more likely to be connected with popular people, which can skew the average by a teeny tiny bit, but it's enough for it to be higher than the number of friends you have. So.
Thank you, great. If there are no other questions, then let's give a big thanks to our presenter.
Thank you.